Hi, everyone, and welcome to the CS Colloquium at the Hebrew University. Today, we're pleased to have David Sontag with us. David is an associate professor at the Department of Electrical Engineering and CS at MIT. Prior to that, he was assistant professor at NYU and a postdoc at NSR, and before that, he did his PhD also at MIT. David has won too many awards for me to list here, including Best Papers Award in various conferences and Early Career Award and such. And today he's going to tell us about learning deep Markov models for precision medicine. And without further ado, David, the stage is yours.
Hi, thank you so much, Roy, for the invitation to be here today. Apologies that I can't be there in Jerusalem, but I do hope to be able to come visit you sometime soon. So the work I'll be telling you about today is joint with several of my current students, Rahul, Zishan, and Rebecca, a couple of my, and Mike, and then a couple of my recently graduated postdocs, Uri Shalit, who is now a professor at the Technion, and Fredrik Johansson, who's a professor at the Chalmers University in Sweden. So as motivation for the technical material we'll be talking about today, I want us to consider a rare blood cancer called multiple myeloma. Multiple myeloma accounts for about 1% of all cancers in the United States, and it's the second most common blood cancer. So it's a blood cancer, which means that the cancer in this particular case is of the plasma cells, which live in the patient's bone marrow. These plasma cells, when they become cancerous, rather than producing normal antibodies, they produce too many of one particular antibody. So in this case, it might be like a IgG or IgM is one of the types of antibodies that a plasma cell would produce. And those antibodies then accumulate in the patient's organs and ultimately lead to a number of complications, things like renal failure, heart failure, and so on. And along the way are a number of symptoms such as bone pain loss that often leads to injuries, anemia, and so on. And it has a relatively short lifespan currently for patients with multiple myeloma because there doesn't currently exist a cure per se, although there are a very large number of drugs that are under investigation, and lifespans have gone from just a couple of years to 10 years or more just in the last decade due to many of the drugs that have been recently on the market. So thinking about this as our running example, what are we going to be seeking to do in today's talk? Well, we want to think about how one both stages the disease and how one thinks about what's going to happen to a patient over the course of their disease. So for multiple myeloma, a common way of staging the cancer is by using what's known as the international staging system. And it's relatively simple. When the patient is diagnosed, one looks at a few simple laboratory test results. For example, albumin is something that's regularly measured in everyone. For someone who is suspected to have multiple myeloma, you would also look at something called beta-2 microglobulin, which is a measure, which is something that's derived from that plasma cell. So it gives you a sense of how much burden of disease that patient has. And in the last decade, it's also standard of care to do some amount of genomic profiling. So you do a bone marrow biopsy, and then you take those plasma cells and you sequence them. And you look at not just the mutational profile, but also what are called cytogenetics to get a sense of the particular genomic abnormalities that that patient has. And then using that information, one can come up with a risk score. So on the right-hand side is an example of a typical plot that you would see in a clinical paper. What this is doing is it's stratifying the patient population by the 3 different stages of this international staging system. For each stage, we're showing a survival curve. So in blue, that's the x-axis is time, and the y-axis here is progression-free survival. So the amount of time until either the patient dies or until they have a worsening of the disease. So the blue curve is where you want to be, right? Those are the patients that are in the lowest risk group. And you can see here that at the time of this paper's writing, 2015, that lowest risk group, 60% of them would live 48 months. But then there's also higher risk populations. So this gray curve is people who are in stage 3. And then for them, the median progression-free survival is just 29 months. So this is typically all that patients get access to. And to try to put this in context, this drives a lot of treatment decisions. So if a patient is believed to be low risk, then sometimes you won't even initiate treatment for those patients, because there's a conjecture that if you maybe start treatment too early for a cancer, then maybe that leads to the patient having sort of multiple clones of the cancer, and the treatment wiping out the sort of the weakest ones, and then the cancer comes back with a vengeance with the stronger clones. And so don't start treatment too early. If a patient is low risk, wait until later, until they start progressing. Right, so that's an example of how these staging systems really affect clinical care. Also, of course, patients really care about this because they want to have a sense of what can they expect in their life. You know, if they're in stage 3, then maybe that's the time that they quit their job and start to spend some more time with their family. So what we're going to be thinking about is first, I guess I want to put this in one more piece of information, put this in perspective, is that I first started learning about multiple myeloma because my mother had multiple myeloma. And this staging system put her at low risk, and everything I just described happened. So her treatment was not initiated. She was being treated here at the Dana-Farber in Boston, which is one of the top cancer centers in the United States. And they followed her over time without treatment. And 3 years into her cancer, it was discovered that she was actually having accumulation of these light chains that are produced by the cancer in her organs. And ultimately, she had heart failure and she died due to complications of the cancer, even before initiating treatment. All right, so this gives us a sense that just having a single score is not good enough. First, because the scores might be inaccurate, right? They might, you're just looking at this very basic information, might not give you a good sense of a patient's true risk. But secondly, because it only tells you one part of the story. It only tells you, for example, how long until recurrence or death, but there are a whole bunch of other multivariate factors that are important for patients with cancer. For example, we'd like to have an understanding of what complications they might be likely to have. In my mom's case, she had what's called cardiac amyloidosis. And so we would like to be able to forecast not just a single outcome, but a whole range of outcomes for these patients and let that guide their decision making. So that's what we're going to seek to do. So we're going to think now about a patient's full disease trajectory, starting from the time of diagnosis, when in this case they'd be assigned a ISS risk score, thinking about their first line therapy, where they would receive one of very many different myeloma treatments. And we'd like to understand how effective is that in any particular treatment likely to be? Is it going to get this patient into remission or not? The corresponding maintenance therapy, if the patient receives maintenance therapy, and again, there are many choices there. When a time of relapse might happen, what the effect of a particular second line therapy is going to be, and what the effect of a third line therapy is usually going to be. And multiple myeloma patients don't typically have more than 3 or 4 lines of therapy before they die. And so all along this way, we'd like to understand not just a single measure, for example, disease burden is the single measure that I'm showing on this slide, but we'd actually like to get a much richer view of how the patient is doing at each of these points of time. We'd like to be able to predict from time of baseline, for example, time of diagnosis, a vector that describes all of the symptoms and complications that a patient is likely to have at each point of time in the future. And if we had that picture, then that could be useful for clinicians to really help guide clinical decision making. And with that, we could ask questions like, like the one I mentioned earlier, how long will patients survive, but also questions about treatment effectiveness. So for example, at this time of baseline, we could try to forecast the patient's future trajectory under one treatment regime or over a different treatment regime. And then of course, depending on which trajectory is predicted, you choose the trajectory that looks most favorable for the patient and guide the patient's therapy with that. So all of this is set up, and what makes working in this area as a computer scientist so challenging is that we just don't have much data to learn from typically. So some of the results I'll show you today are coming from a publicly available data set derived from the Multiple Myeloma Research Foundation, and has data on over 1,000 patients. Now, 1,000 might sound like a big number, but there's so much heterogeneity in this population in terms of the different treatment strategies patients are on, but also on their underlying genomic heterogeneity, that is actually not that much data. There might be only 1 or 2 patients like any single patient in that data set. Moreover, data like this tends to have a ton of missingness. So on the bottom, I'm showing just one example of hundreds of observations you have available in a patient at any point in time. This is coming from a patient's lab test results. And blue is an example of whether it's observed, red is missing. So here you see only 2 time points are missing for this particular observation. But that's because this is a highly curated data set. If you were to take data derived from electronic medical records, as we'll talk about much later, you tend to have much more missingness in the data. And I was mentioning the treatment strategies themselves are highly complex. So here you see how a patient might have 3 different lines of treatment, but even in a single line of treatment, that might involve a combination therapy. So here I'm showing that this particular line of therapy involves these 2 treatments that were administered for this particular patient at these time points. And there's variation even in that. So if there are any questions, by all means, feel free to unmute yourself and ask me questions. It's a lot of setup, but now's a good time.
Can I ask something?
Please.
Yeah. So is there any kind of clinical view of this graph saying if you are really about to change from line 1 to line 2, increase the, I don't know, the daily measurements of blood or something like that, so that the decision, I don't know if the decision, but at least the data behind the decision is more dense and more complex, and is it really infiltrated to the clinical aspect of the game? Yeah.
So, Michael, I think there are a couple of different aspects of your question that are important. The first one has to do with, can we change practice to get better data for computer scientists, right? For example, if you have a patient with an autoimmune disease, you might try to gather data before they have a flare-up. For a patient with cancer, gather more data right before, right after initiating treatment. Mm-hmm. That's seldom done, and the reason is mainly cost. That's the main one. In the United States, at least, someone has to pay for the healthcare. That's a health insurer, and they don't care about research. They care about doing the bare minimum to take care of patients. But then there's a secondary problem, of course, which is that some of the data for patients with multiple myeloma come from the blood. But some of the richest data comes from a bone marrow biopsy, which is extremely painful. So, for example, the genomic data that we have available is usually only at the time of first treatment, and sometimes there'll be another bone marrow biopsy at the time of a recurrence. But because it's such a painful activity, it's not done that frequently. There's a second subtlety that you were hinting at, which is also very important. And that's that the data itself is very biased. So it's biased by what clinicians are thinking and by what's going on with the patient. So even the missingness properties of the data are a function of how the patient is doing. If the patient is doing really well, the doctor might say, come back again in 6 months. If the patient is doing poorly, then they might be following the patient every couple of months and observing their blood test results, for example. And so when the data is missing, it's definitely not missing completely at random. Thanks for that question.
Absolutely.
All right. Mm-hmm. Okay, so what I'm going to propose. Yep, please go ahead. Yep.
Sorry for staying behind the camera. Yeah. You are assuming that you do have an objective measure of the disease progression, right? Something like ground truth that you do have.
That's a great question. Yeah, thank you for that question as well. So yes, and that's been for this and for many other diseases, there are validated measures of how the patient is doing. So for example, for multiple myeloma, because it's a cancer of the plasma cell, you can figure out what type of cancer they have, in particular, which particular immunoglobulin is the one that's overexpressed for that patient. And then you could track that amount over time. So for this patient, IgG is the particular immunoglobulin type that is abnormal for them. And that could be, it's produced in the bone marrow, but then distributed throughout the blood. And so you can just do a blood test result to get a sense of how much there is. And that gives you a sense of disease burden. But that already starts to hint at one of the limitations of existing methods for disease progression modeling, which is that prior to our work, most methods focused on a single measure. So just like in this picture, you might imagine forecasting the patient's IgG values from baseline over time. And that gives you a very incomplete view of how the patient is doing. So I mentioned to you earlier how sometimes patients might be having complications of their disease, and those complications themselves might be risky and might need to affect treatment strategies. And so one of the big shifts in thinking from the work I'll be describing to you today is that rather than modeling just a single disease burden measure, such as serum IgG shown here, we're going to be thinking about the full vector of observations that a patient could observe at any point of time, and we're going to in essence impute the patient's full medical trajectory. So everything that would be written in their electronic medical record, we're going to be forecasting, and that is going to be giving us a much richer view of what's going on with the patient.
Can I also ask a
small question? But it's also
question?
a much more complex modeling problem. Yeah, go ahead, Nadav.
So how do you treat like the time scale? Like, do you assume that you have predefined time points for which you should have measures, or like do you treat it as something continuous? Like, how do you model that exactly?
So in some of my earliest work, we treat it as continuous time processes, where we'd say, okay, some amount of time would go into an observation. But for the work I'll be telling you about today, we treat it as discrete time. So for example, this particular data set we'll be working with has data collected at 3-month intervals, and that's because it's not quite an observational data set coming from the real world. There was actually a clinical trial run where the clinical trial wasn't comparing different treatments, but it was gathering data on patients. So clinicians would just treat the patients as they would usually, but they would report back to the data gathering agency every 3 months. And so we would have observations every 3 months. And so we just use a discrete time model for this. But really one can consider both, and the technique I'll be telling you about today would generalize if you have varying time intervals between observations. That time interval ends up feeding into your transition distribution. These are all great questions. Other questions?
One question about the genetics. So what is actually measured? Do you have karyotypes or specific mutations or both?
So for patients who are not in a clinical trial, standard of care would be to do what's called a FISH test, where it looks at what translocations the patient might have present. And in some cases, one might also look for particular mutations. But it's increasingly becoming standard of practice, particularly in any research study, to do just full RNA-seq on these patients. So you would select out the plasma cells from the bone marrow and then do either bulk or single cell sequencing on them. And so the data that I'm describing here has that bulk RNA-seq data. And my student, Rebecca, is also doing quite a bit of work with single cell data, although I won't be reporting on that here.
But then it doesn't show rearrangements.
That's a good question. I think in many cases one can infer that from the data. That's what we found, and I think there are additional observations that are done to get arrangements. I'm only telling you part of the data that's used.
Thanks.
Okay, so as I've been alluding so my approach shouldn't be surprising, right? So I've been alluding to what we're doing all along. We're going to take a patient's data and we're going to learn a model of how the patient's state evolves over time. The true patient state we might not ever be observing, so it's going to be latent variable and we get noisy observations of it from the clinical data. And we're also going to want to model how interventions such as medications affect that patient's state across time. Towards the second half of today's talk, I'll start formalizing this from a causal perspective, and I'll show you how to use causal lens to both talk about the assumptions, that one's going to need in order to ensure a valid predictions of treatment response from observational data. And the general algorithm I'll be telling you about is interesting in its own right. It's interesting even outside of a healthcare setting as a learning algorithm for high-dimensional nonlinear time series. And so the model looks a little bit like this. It's a Markov model in its essence, a hidden Markov model in its essence, where we are going to say that a patient's state at any point in time is denoted as ZT. That state is unobserved and is evolving with time as the patient progresses in their disease. Now, a bit of a distinction from typical hidden Markov models is that we're going to assume that this state is continuous valued high dimensional random variable. So for example, it might be an R to the 100. And learning is going to discover the meaning of that patient state. It's not something that we're going to presuppose for the learning algorithm. What we observe at any one point in time, of course, is not the true underlying patient physiology, but what we can observe from laboratory tests and so on. And so that's what we're denoting as these X variables, also evolving with time. And the edge from Z1 to X1, from Z2 to X2 simply denotes that we're assuming that the observations at any one point in time are a function of the underlying latent patient state. And we also have, of course, actions or interventions, which I'm denoting as U in these pictures. The clinician is choosing different interventions, whether it be a particular combination treatment therapy or surgery at each point in time. And our assumption is that those actions are going to then impact or cause a change in the underlying patient state at the next time point. And I'm showing you a simplified graph. You can imagine adding many more edges here to denote more complex relationships. So there are a couple of things I want to call out before I go into some of the details. The first is that here we're going to be modeling the full vector of observations at each point in time. And that's in contrast to most previous work on disease progression modeling, where you would focus on, for example, a single measure of disease burden and project that across time, usually using something like a Gaussian process. So we're not going to be doing that here. The second thing to note is that how a treatment affects the underlying patient state could be something that's highly complex. And so this transition distribution from the patient state at one time point to the patient state at the next time point as a function of treatment we should expect to be a complex nonlinear function. And so we're going to need some way of learning those complex transition distributions. And then, of course, there are some number of other observations we can make already at this stage. So, for example, this model is going to be highly non-identifiable because of our choices, for example, of ZT living in R100. For example, you could just rotate the latent space, you could scale the latent space. There are all sorts of changes you could make, and you get the same underlying joint distribution. And so, we can't hope that the latent space is going to have any particular meaning, and rather we're going to have to think about new ways of reading out from a model like this. In particular, we're going to be using the observations as a way of reading out. So you want to have understanding of how a patient is doing at time step 4? Well, let's look at the posterior distribution over X4, for example. And that's how we're going to try to interpret projections from this model. So because of the, and so once we have this model, we're going to use it as an in silico model for assessing the effect of interventions, in essence by forward sampling in this model. Now, as I alluded to, these transition distributions, one would conjecture, should be highly nonlinear. And so we need some flexible way of modeling them. And the most naive way of doing so would be using a deep neural network. So one would take as input your latent state, ZT-1 at the previous time step, and the action taking at the previous time step. Our actions, by the way, we're going to be modeling as a vector. And that's very convenient, particularly when you have these combination therapies, because then you can, in essence, indicate which of several different drugs are being given at that point in time.
Well, then question?
Yes, please go ahead.
So the action encoding is one hot vector. Is it just an indicator vector indicating which actions were given, or something more complex?
To start with, you could think about it as just what actions were given. It won't quite be it'll be one hot vector, which is not necessarily, which is sparse, but is not a sparsity of 1. I'll have a sparsity of greater than 1. We're going to talk in about 10 minutes. I'm going to give you a more complex action encoding, but for now, assume it's that.
Maybe I could interrupt also.
Please, yeah.
Is the reason why X doesn't direct U?
That's a great observation. X, in fact, does impact U. Z probably impacts U as well. Right. Said differently, the clinician actions are not just flipping a coin, but they're actually a function of what's been observed for the patient, some of which hasn't been written down. That's why I said Z might as well. I'm going to be ignoring that subtlety right now, and I'll be coming back to that in the second half of the talk. Thanks for asking. Okay, and so for those of you who might have not seen these things before, just like one would do in a what's called a variational autoencoder, a type of deep generative model, we're going, after applying a number of nonlinearities to these inputs, we then get a mean vector that's described by this nonlinear function g, and then we're going to sample from a Gaussian distribution with the mean given by that g function. And that's going to then introduce some stochasticity into the transition distribution. And so this is work that my lab started in 2015. Now it's somewhat commonplace to see this merger of generative models and deep learning. The Z's are the random variables, and we use, in this case, the nonlinear relationships show up both in transition distribution and in the emission distributions of this hidden Markov model. And I want you to be having in the back of your head what might have been a counterpoint, the most naive way of modeling this multivariate time series, which could have been using a recurrent neural network, right? So all of you should be asking me, why not just use a recurrent neural network to model this distribution of x's across time? Why do we need to bring in the stochasticity through these latent variables? And I'll return to this throughout the talk, but the short answer is because by making the conditional independence assumptions that are implicit in this graphical model, we're intentionally limiting the model capacity. And that's going to have a really big impact in terms of our ability to fit these models from limited data sets. And we find time and time again that recurrent neural networks overfit the data we have, whereas these models we can tend to fit reasonably well. Okay.
Can you say a few words about the architecture that you're using, whether
Sure.
you're just using a feed-forward or something like LSTM, which is more specialized for this kind of time series?
Yeah, so thank you for that question. First of all, there is not a deterministic hidden state as you would have in a recurrent neural network, right? So what you're probably asking me about is what is the form of the G function? Is it just a feed-forward multi-layer perceptron or something more complex? One could use anything. In the paper that I have here in the bottom left, we suggest using a gating type architecture similar to what you would find in a gated recurrent unit. But very shortly, I'm going to be telling you about a slightly more intelligent parameterization for this based on pharmacodynamic models. So I'll come back to that in a minute.
Another quick question.
And so, please. I'm going to very soon have to slow this down for questions to make sure I get to the material. But give this last one shy, and then I'll slow this down. Then I'll start speeding up for a bit.
Yeah, this will be the last one. This looks somewhat similar to the input-output HMM. What is the difference?
So an input-output HMM, if I understand correctly, has inputs like these actions use and these outputs like these X's. And so that's why I said at its basic element, this is just a hidden Markov model, or there's these action components, Kalman filter, and so on. Where things interesting start happening is the actual parameterization. So the fact that these Z's live in this high dimensional continuous space and that we have these nonlinearities described by neural networks, that's where the differences start coming in. So not by the basic graphical model, but by the actual parameterizations.
Okay. I think that originally they also described some of it as neural networks, not deep. At that point, they didn't talk about deep, but still non-linearity was there.
Yeah, and I'm going to come to that in my next slide. So the question is, how do you learn these models? And as Shai just mentioned, there is extensive literature on learning stochastic nonlinear dynamical systems with many different learning algorithms. What makes learning challenging here is that the Z's are unobserved, whereas in much of the literature there, the assumption is that your latent space in your training data is observed, and the high dimensional aspect of this also makes it very complex. And so many of the learning of the earlier learning algorithms in this space, either based on Markov chain Monte Carlo methods, or even methods based on variational inference, as we'll do here, just didn't scale. And so what we're going to be doing here is putting, in some sense, a modern lens on how one can learn models like this. And in the paper, we compare to many of the earlier learning algorithms that I mentioned, which didn't scale at all and tended to work just with extremely small dimensions. And so the general approach we're going to take is to use stochastic gradient descent on a variational lower bound on the likelihood. The reason we use a variational lower bound is because these Z's are unobserved, and even evaluating the likelihood where you marginalize over the Z's is in itself an intractable problem. And then we're going to use so as part of the variational lower bound on the likelihood, which we want to maximize, we're going to use one needs a approximate posterior distribution for every data point. So given a set of X's, you need to be able to approximate the posterior distribution over the Z's given the X's. And we're going to be approximating that using bidirectional recurrent neural network with a particular structure that I'll tell you about in the next slide. And doing so leads to two major advantages. The first is that we have a very fast algorithm. So this approach I'll tell you about, for example, uses 50 times less memory than a traditional approach. And it's also very flexible. So our learning algorithm could be written down in 2 or 3 lines of code now. And the particular details of the transition distribution, the mission distribution, are somewhat irrelevant. The learning algorithm will work for any transition of emission distribution, and that's going to be advantageous, as I'll show you about in just a few minutes. So because this is a Markov model, we know that the posterior distribution has a particular structure to it. So we can write that the posterior distribution over the full vector of z's at each point in time for a data point xj can be written as sum q of z1 for the first time step times a product for each of the subsequent time steps of zt conditioned on just zt minus 1. So because of the conditional independence properties, you can ignore, in essence, all of the previous values of the z's. And of course, conditioned on the full x vector as well. And so as we build up this recognition network, which is going to take us from our x's, and we're going to then, instead of solving a complex inference problem to get the posterior distribution over the z's given the x's for every data point, we're going to, in essence, compile inference, and we're going to give a deterministic algorithm that very quickly goes from x's to a posterior distribution over the z's. And the way it does that is it's first, and this is during learning. So during learning, we assume that we observe full sequences of the x's during learning. And so we take a recurrent neural network. Now this is going to be a typical recurrent neural network. We're going to do a left to right encoding of the sequence x. And we're also going to do a right to left encoding of the sequence x. And then we take the hidden state at each point in time, and you combine them in order to get in order to make a prediction of the posterior distribution of the patient state at that point in time. So all of that would be ignoring the particular structure of the distribution. But notice that I showed you that the true factorization of the posterior has this simple form where the zt should depend on zt minus 1. And so we're going to use that knowledge of the form of the posterior in order to add an additional edge here from zt feeding in to zt minus 1. And that goes by what we call a structured variational approximation. And that ability now to model the posterior distribution using a form which we know actually is representative of the true posterior distribution substantially improves the quality of learning results, as I'll show you about next. Okay, so that's the learning algorithm in a nutshell. First, I just want to give you an evaluation in a non-health setting to give you a sense of the complexity of models that can be learned using this modeling approach. So here we just took a data set of music, of Bach chorales. At each point in time, we have 88 dimensional vector, which are the keys of the piano that are being played. And we're going to take these sequences of length corresponding to the number of seconds of the song, and each point in time, an 88 dimensional vector for what keys were being played. We're going to learn the model I just described on that data set. And then we're going to look at a couple different things. One aspect we're going to look at is how well we can model unseen data. So what I'm showing you here on the bottom is for 4 different music data sets. We're just looking at our held out likelihood or a lower bound on our held out likelihood from the deep Markov model compared, in this case, I'm just showing a subset of our results comparing to the best recurrent neural network we could learn at the time with the best choice of architectures, with the best choice of learning rates and so on. And what we found time and time again is that these deep Markov models tend to generalize much better than a recurrent neural network. And that's because of those conditional independence properties that we're assuming. The second thing I'm going to do is, if my mouse lets me, I'm going to try to play for us the video. Let's see. One moment. It might not let me. Let me stop this for a moment. Can you guys still hear me? I'll just hit play now. Do you hear that?
Yes, yes.
Okay, great. So this is just an example of a sample from the model after it's been learned.
I think we can't hear the music, just you.
Oh, you can't hear the music?
No, we hear you.
Oh, okay.
But the music.
Only you.
Ah, okay. There we go. This should work. Can you hear now?
Yes.
Okay, so again, my only goal there is to hold on. That's definitely not the best music generator, but the point is just that it's able to learn some complex signal in the data, right? Now, the next thing we looked at is, are we able to learn the effect of interventions? And so for that, we're going to first look at a synthetic data set that we created. We call it the healthy Mnist data set. In this data set, we have patients being digits. So for example, patient 1 is a 4, patient 2 is a 3, and the interventions, the U's, are going to correspond to rotations to the patient. So U is just going to be now a single dimension, and it's going to be given as a number, which is just the number of degrees of rotation, positive or negative. And so I'm not showing you what the U is, but you can see that going from time step 1 to time step 2, it looks like there was a negative certain number of degrees rotation to 4 and so on. Now, real patient data, of course, a little bit more complex. So we're going to make the training data a little bit more difficult. First, we're going to add observations that have nothing to do with the interventions themselves. So for example, this patient might get a cold at time step 3. That cold is denoted by a white square shown in the top left, and it deterministically lasts 3 days. So that's why you see it lasting 3 different days and then goes away. And that has nothing to do with the underlying intervention. We might also not be able to observe the patient state quite so cleanly, so we're going to add a bunch of noise. So we're just going to add 20% bit flip noise. And now the actual observed data looks a little bit like what I show on the bottom. Those are the X's. All right, so we have these sequences of these X's, X's comma U's. And what we want to figure out is, can the learning algorithm discover the meaning of these interventions U just from this data? And the first thing we see is that learning does a reasonably good job of inferring the underlying patient state. I told you the way that we read out from this model is by looking at the posterior distribution over the axis. And you can see here now, taking as input of, in essence, trying to clean the sequence, the model is able to clean the sequences pretty well. The much more interesting question is about whether the models learn the meaning of rotations. So here what we're doing on the top, we take an input, a single digit input, and here we take the clean image and we simply apply a fixed U vector, U across periods of time. So for example, we try to force a small rotation to the right, we force small rotations to the left, even though that particular sequence of small rotations to the right or small rotations to the left has never been observed in the data set. We are going to see whether we've learned the meaning of the intervention by just trying to do forward sampling under a fixed pre-specified intervention vector. And we see that the model has in fact learned the meaning of that. And you can see other examples here. So this is just to say that the model can learn the effect of these interventions even from very noisy data. Now let's get to something which is a little bit more interesting. Now we're going to take a real data set coming from the Multiple Myeloma Research Foundation. These are 1,000 patients treated according to standard of care. We're going to model 16 different biomarkers across time, including measures that are typically used to measure disease burden, but also many other measures that are of clinical interest. And our U, or action vector, is going to look at several indicators of treatment. Unfortunately, even the model that I just showed you, so recurrent neural networks are impossible to train on this data set. They overfit immediately, no matter how you try to control their complexity. but deep Markov models also overfit in this data set. And so what we needed to do is introduce a new method, sort of one step further, to try to control the capacity of this model. And our method of doing so is by using some prior knowledge on what treatment does in this setting, in this cancer setting. So there's been quite a bit of literature on modeling the effect of drugs on patients. So the pharmacodynamic community typically models the effect of a drug on a single measure of a single biomarker across time, usually with a differential equation type model. And that's not quite enough for us. So one might think you could just carry over the differential equations used from the pharmacodynamic literature, but it's insufficient for two reasons. First, because there doesn't actually exist any pharmacodynamic model for the treatments that I'm telling you about here in a blood cancer setting. Most of the models that exist are for solid tumors. And secondly, because we don't want to just model the effect on a single biomarker, we want to be modeling the effect in latent space. And so the key question is, how can we, in essence, model the effect of treatments now in latent space? And to do that, we introduced a number of these transition distributions. So these are the same G functions we showed earlier, where one of the questions I was asked was, do you just use a feed-forward network for that transition distribution or something else? Well, this is what we actually use in practice. And these equations, I'm not going to go into the details, are all motivated by the pharmacodynamic literature. And so the way in which the interventions you impact the latent space of the next time step has a very particular structure to it, which I'm not going to get into the details of for reasons of time. And in our upcoming ICML paper, we show how one can learn a deep Markov model with that particular transition distribution. And that does tend to work pretty well for data of this sort. So as a simple illustration of that, here's an example of one patient. We're going to look at the particular treatments that were proposed to be given for this patient. So we're looking at just the first line of therapy. That's what this red bar at the top means. And at time step 1, they're proposed to receive these 3 treatments: BOR, DEX, and LEN. And then LEN is continued to be given at various time points going to the future. And we're going to condition just on the first time steps observation here. So here we observe the patient biomarkers at time step 0, and then we're going to sample into the future. So we're going to, in essence, project forward what the patient's data is going to look like for the next 20 months. And in blue here, I'm showing the actual patient data, what was truly observed. And in red and in gray, I'm showing the predicted data, again, using data just at baseline. So you see at time step 0, these two align. That's because we're conditioning on the data at time step 0. Now, if you use a transition distribution which is linear in nature, and that tends to be the best that you can fit from the limited data that you have, it doesn't do very well in matching the observed data. So you see, for example, looking at the patient serum lambda, it sort of after time step 1, there's a huge drift. On the other hand, what we found time and time again is that using these PKPD inspired transition distributions, we do a much better job at forecasting the patient's actual data. Here's a second example where now we take the patient data not just at baseline, but the first 15 months, and we try to project forward. And so the first 15 time points, or 7 time points, are matched up, and now we're projecting forward the patient's data. And again, we see a pretty decent match to what actually was observed for the patient. So in summary from this first part of the talk, I gave you a time series model. I argued that deep Markov models have much lower sample complexity, and that's one of the main reasons to want to use them, in addition to many of the other advantages, such as the ability to deal with missing data elegantly by marginalization. And I showed you how we use domain knowledge to parameterize effective interventions. But there was a question very early in the talk, which was, shouldn't there be edges from the X's to the U's? Because in actual patient data, the U's are not drawn independently. They're a function of what we observe for the patient. And that's what we're going to get into for the last 8 minutes of today's talk. So in particular, our goal here is to take data that's just captured as part of the practice of medicine and use that to try to learn models like these in order to improve any patient's cancer trajectory. The reason this is important is because less than 5% of adult cancer patients participate in a clinical trial, but the other 95% do leave an evidence trace. So in the United States, for example, well over 85% of hospitals have electronic medical records, and there's some record in that of what treatments patients actually received. And so what we'd like to be able to do is take that observational data and learn deep Markov models that would then allow us to ask counterfactual questions, such as, for example, here's Anna, we have some data on her at baseline, and we want to predict what would happen to Anna under these two different treatment regimes, t equals 0, t equals 1, going to the future. And if the y-axis here is some measure of disease burden, we would say we prefer t equals 1 because t equals 1 obtains smaller disease burden. So this is what we'd like to be able to do. And for simplicity for the next few minutes, what I'm going to do is I'm going to suppose that we're only looking at a single point in time. So you could use a deep Markov model, but if you were to take, let's say, the 4th time step in a single biomarker, and we'll call that y, we want to know what is the effect of x on y. That's just to this one time step view is going to make it very easy for me to explain some of the subtleties that arise when trying to do this prediction of treatment effectiveness. So the way the machine learning community typically handles this problem is to take the observations you have and to build a model, some function f that takes as input both the features for the patient and the treatment choice t, and learns to predict that outcome y. So if f is given to you by a deep Markov model, then we'd be marginalizing over all of the z's in order to predict some outcome y. And so that would be the form of f. But f could just be some random forest, for example. So one takes your observational data, which consists of patient features, the treatment they actually received, and their actual outcome, and you fit some model f to it, which tries to estimate the expected value of the outcome y given x and t. And then once you have that, you could, given a new patient, you could compute what's called the conditional average treatment effect, where you take your function f, you plug in 1 to try to predict what would be the effect of taking treatment 1, you plug in 0 to try to see what is the effect of taking treatment 0, you take the difference between those two predictions, and if Kate is positive and having a large value is good, then you give treatment 1, otherwise you give treatment 0, and vice versa if having a small value is good. So that would be the way in which these models will be used to guide treatment choices. And so there are a number of assumptions that need to be made in order for this to work. What I'll be telling you about is are those details. So in particular, remember, if our goal is to try to guide treatment suggestions, then for each person, we might want to know not just, we might want to predict into the future what would happen to them if we give them treatment 0. So that would be evaluating the function f of x David, comma 0, because the second argument is the proposed treatment. We might also want to know what happens to them if we were to give them treatment 1. So that would be looking at f of x David, comma 1. So at test time, we're interested in knowing the predictions for every value of the treatment, because that's what we need in order to choose among the treatments. In particular, we want that our test error be low, in this case, on all 6 times 2, 12 predictions, because we're predicting both treatments at test time. Now, the difficulty that arises is that your training data comes from data of patients who got actual treatments, and each patient only got a single treatment. So our training data looks a little bit more like this. So if David only received treatment 0, then our loss function during training can only look at how well we're predicting for f of x comma 0, because we only observe treatment 0 for that patient. If Mary, on the other hand, received treatment 1, then our loss function during training would look at how well f of x Mary, comma 1 predicts the y for Mary, right? And so you can start to see a mismatch here. If your training if your training distribution looks like this, and if your treatment assignment was not flipping a coin, then you now have that your training distribution doesn't look like your desired test distribution. And that's going to be a big limitation into when one can actually do these predictions of treatment effectiveness from observational data. Formally, this goes by the name of covariate shift. So what we're going to do now is we're going to combine, just to formalize this mathematically, we'll combine the patient features X and the treatment choice T. I'm going to call that X tilde. The training data is drawn from this distribution P of X tilde comma Y. And your desired test distribution, I'm going to call that Q, is drawn from a different distribution, Q of X tilde comma Y, where Q of X tilde given comma Y, if you were to expand it, it has the same distribution over X as P, because the patients are coming from the same distribution. And Y given T comma X is also the same. If you're to give a patient a treatment T, we're assuming that what it does to a patient is the same training to test. The really big difference is the treatment assignment mechanism. In training data, there might be existing clinical practice decides some treatment to give patients. So that's P of T given X. And at test time, we're interested in knowing what would happen under all treatment. So Q of T given X, you could think of as just being a uniform distribution over the two treatments. So Q of T given X could be, let's say, 0.5 probability of 1, 0.5 probability of 0. And that's the big difference. And so what we want to know is if you're to train on P and then test on Q, when can we expect there to be good results? And there's a trivial theorem, it's a couple of lines to prove, long known in the community, that says so long as P of X tilde is non-zero whenever Q of X tilde is non-zero, and so long as the conditional distribution of Y given X tilde is equal to the conditional distribution of Y given X tilde under Q, then a limit of infinite data, you can achieve the Bayes error. You can get as good prediction as possible. And this is an example of what's called covariate shift. And the key assumption is this overlap assumption. And so what one needs to know is, does there exist X with P of X greater than 0 such that in your training data, the treatment assignment mechanism is deterministic? That would be a violation of this overlap assumption. And if that happens, then all bets are off. You would never be able to say what would happen to a patient under the corresponding treatment regime. So here's a simple example of that. So suppose that all men received treatment 1 and had some outcome, let's say Y equals 1. And suppose that all women received treatment 0 and had some outcome, let's say Y equals 0. If your training data consisted of many different copies of that, and then if you were to ask what is probability of Y given X equals 1 comma T equals 0, or what is the probability of Y given X equals 0 and T equals 1, because you never had a man receive treatment 0 or a woman receive treatment 1, those two conditional distributions are completely unconstrained. And so you can, if the truth is one thing, you can artificially set this to be something else, and you see that you can achieve arbitrary error, and it would be impossible to do prediction under that setting. And so what's important is that we can guarantee that in your observational data set, you have common support, which would prevent that from happening. So long as probability of treatment is always bounded away from 0 or 1, then you can guarantee generalization with enough data. And I know I'm running up on time, so I'm just going to present 2 more slides and we'll start wrapping up. And so that is an important assumption that one needs to test. And if we want to achieve this dream of being able to use observational health data to actually guide patient treatment suggestions, we need to have confidence that our predictions are actually going to be valid. And so, for example, we might want to restrict ourselves to comparing treatments only when there's overlap. And so, for example, in this recent paper in AI Stats, we showed how one can formulate this problem of describing the overlap region as an integer linear program, where we're trying to describe the set of points X such that the probability of treatment given X as estimated using machine learning algorithm is always bounded away from 0. We want to describe it as simply as possible. We solve a relaxation of that problem, and I'll show you an example of what the output looks like. So here, consider, again, patients with multiple myeloma. And let's think about two different treatment strategies, ASCT, and so giving an autologous stem cell transplant and not giving an autologous stem cell transplant. Those are two different possible treatment strategies. In reality, patients who are relatively elderly, older than the age of 77, are usually not considered as eligible for receiving that second treatment strategy. But we don't necessarily know that. What we'd like is to come up with is that our learning algorithm will output a region which describes what is the validity region where you could imagine asking about the different treatments. And so we take as input, data that looks like this, shown at the very bottom. Number of different lab results and demographics, risk scores at baseline, and we want to know for which distribution of patients would they have been able to see both of those different treatments in the observed data. And here's an example of the problem that arises. So here, if you were to look at even just a single feature like age, for people who are very elderly, they tend to not receive the autologous stem cell transplant. For people who are very young, they tend to only receive autologous stem cell transplant. So that would be an example where for either very young or very old, we would never be able to talk about what the counterfactual is. And so our learning algorithm will output, it'll output either conjunctive normal form or disjunctive normal form description of the regions of space where you have overlap, which one could then take together and give to a decision maker. So the decision maker then could, when using, let's say, a deep Markov model, would only ever ask about the treatment regime for which you have overlap, because the model cannot be trusted in any other setting. And so I recognize I'm out of time, so I'm not going to talk about the second aspect, and I'll just wrap up. So in summary, there are a couple of assumptions that one needs to make in order to be able to infer treatment effectiveness from observational data. Overlap, and a second thing called no hidden confounding, which I didn't have time to talk about. And we've been practical methods now in order to both assess overlap, in order to also show robustness to hidden confounding, and those two are going to be really important. So I know I'm out of time. I'll stop there. Thank you very much.
Thank you. So thank you very much, David, for a very interesting talk. I think given that we're out of time, if people have questions, they can reach out offline. And see you all next week. And thanks again, David.
Thanks so much for having me. Bye, everyone.
Thank you very much.